let's look at another interesting problem. What I have here is a bucket of water, okay? A bucket of water. And what I'm going to do is I'm going to spin it. I spin it about the central axis of the bucket. You know, assuming it's just a cylindrical bucket. So what happens? You know, the water surface is going to curve. It's going to curve up, right? Like this, right? And what I want to know is what exactly is the shape of this curve? That, of course, depends how fast you spin the bucket. Let's say it spins at a rate such that it takes a time t to complete one revolution. It takes a time t to complete one revolution. We know, common sense, the shorter the time, the more it's going to curve up. Okay? But exactly what is the shape of this curve? Here's a cross-sectional view, of course. Gee, you wonder how you would do a problem like that. But because obviously different parts of the water will undergo different amount of acceleration, right? Say on the central axis, it's not accelerating at all. But you look at any arbitrary piece, like say this piece right here, it's doing a circular motion, right? About this center right here. Everybody is doing a horizontal circular motion. But even though you turn around at the same time, t, you don't have the same acceleration because the acceleration goes like v squared over r. You have different v, you have different r depending on where you are. So again, just like we learned in the previous problem, when an entire piece has different acceleration throughout its body, we cannot think of the entire piece as a single system. We must break it apart. We must take a small piece out of it so that we can apply Newton's second law to this little piece which has only one value of acceleration. The question is, where is that small piece going to be? Well, remember, we're interested in the surface, okay? We want to know the shape of the surface, right? So, do you think it's a good idea to look at a point somewhere in the middle, inside water? It's probably not going to help us figure out what happens there, okay? A better thing to do is to find a piece right on the surface, right? Why not? Right on the surface. And we want to know the orientation of this surface. So why don't I pick up a little piece like this then? Okay, I'm going to pick up a little piece right here. It's like a little slab, very thin slab. Let me analyze the motion of this little thin slab. You know, I don't know what its mass is, and I don't know how much force is exerted on it because I don't even know its mass. So how can I find the gravitational force and so on? It looks like an impossible problem, but don't worry, let's do it. We have this little piece. Let's say the mass is dm. Okay, of course we can draw a free body diagram now. This is dm times g, right? What else? That's the contact. That's the non-contact force. So what about the contact force? Well, it is being pushed by the surrounding water from all sides, but it's such a thin slab, so I'm not going to worry about being pushed from the side because the area is so thin. This bottom surface, that is where it received the greatest push, and that is a normal force, like this. Okay, let's call it dn. dn. I do not know the magnitude of dn, but I do know that it's perpendicular to the surface of the water at this local position. Okay, as a result of these two forces, this slab of water is doing a circular motion about this point, O prime, which has the same horizontal level as the piece itself. So it's doing a circular motion like this, right? Doing a circular motion like this. It has a radius from here to there, and let's say the coordinate of this point of this slab is x and y. So what is the radius then from here to there? Isn't that just equal to x, right? Yeah, that's just equal to x. So, and let's say here's a vertical line. This angle is theta. Now you agree this is the same angle as that angle theta, right? Because I have two pairs of mutually perpendicular lines, horizontal, vertical, and then I have tangential and normal, so these two angles are the same. Okay, let us apply Newton's second law to the motion of this little slab. What I have horizontally is a circular motion, and vertically I have no motion. So the vertical part is simple. Let's do that first. The net force in the vertical direction is 0. So I have dn times cosine theta. That's a normal force upward component. That must cancel with the gravitational force downward. That must be equal to dm times g. Okay. Horizontally, the net force is not zero. It has to provide you with the centripetal acceleration. So the normal, you have dn times sine theta. Dn times sine theta. Inward, that is the only force that can give you centripetal acceleration because it's the only horizontal component. What is the centripetal acceleration? The centripetal acceleration is m dm, the mass dm, times ac. Okay, this is the centripetal acceleration is ac. We can find ac. We can do that. What's ac? ac equals v squared over r. What's v? v is the speed of this little slab going around, right? What is its speed? v squared over r is x. Okay, the speed is such that it covers a distance, total movement distance of 2 pi x over time t. So you take circumference over t, you'll get the speed 2 pi x over t, right? Squared over x. So I find the centripetal acceleration to be equal to 4 pi squared x squared over x, that's just 1 x left, over t squared. That is the centripetal acceleration, which I can plug into here. Now, I don't know what dn is, nor do I care. I don't know what dm is, the mass, nor do I care. I do want to know what this angle is, because if I know what this angle is, that gives me a clue as to what the shape of this curve is, right? This angle, after all, tangent of this angle is the slope of the local curve here. So therefore, I want to solve for theta. How do I eliminate dn and dm in one gulp? Yeah, I can take the division, okay? I take this guy divided by that guy. Then I get sine over cosine, dn is gone, right? So sine over cosine, I get tangent, theta. The other side, dm is gone. What I get is ac over g, right? ac over g. ac is right here. So I get 4 pi squared x over t squared, that's ac, and then divided by g. Okay, so even though I didn't quite find the exact shape yet, but I do know that tangent theta, which is the local slope of this curve, equals 4 pi squared x over t squared g. It is not a constant. It increases as x increases, which means the slope is going to increase, okay? Otherwise, if the slope is a constant, you get a straight line, which doesn't make any sense. It actually increases like this as you go out. Now, I want to know y as a function of x. Can you express tangent theta, the slope, in terms of y and x? Well, it's common sense that this is equal to dy over dx, right? That's how you find the slope. So now we have dy and we have dx. I'm interested in y as a function of x, so what I'm going to do is I'm going to integrate. Okay? Let me solve for dy. I have dy equals to, dy equals 4 pi squared x over t squared g, and then dx, right? I have only y on this side, only x on that side. I have separated variables, so I can now integrate to get y as a function of x. Let's take a good look. You start from 0. That's when x is 0 and y is equal to 0. So both x and y are equal to 0. To a certain location here, x and y. So this is x, this is y. Okay. The integral is rather easy to do. So let's do that. Y, 0 to y dy, so that's just y. The other side, 4 pi squared t squared g. That's just a constant. Okay, what's left is x dx, right? X dx. It's 1/2 x squared, of course. So when you work it out, you find it is equal to 4 pi squared t squared g times 1/2 of x squared. Okay, so we conclude that y is a constant times x squared. Now, by the way, what kind of function is that? Y is a constant times x squared. Yeah, it's called a parabola. And if you go take a look at this, you know, it makes sense that this thing can easily looks just like a parabola, and it turns out it really is. Okay, it's a very simple curve, and we found what it is. In fact, I can write this as y equals kx squared. That's a typical parabola. And what's that k equal to? K is that constant in front of it. It's 4 pi squared to gt squared. Take a good look at this constant. Okay, see if it makes sense to us. 4 pi squared is a constant, 2 is a constant. It is inversely proportional to g. What does that tell you? If g is very large, k will be very small. When k is very small, then, you know, when you plot y as a function of x, when k is very small, you get a very small rise like this, very small, very slow rise. Does that make sense? Yes, because, you know, in order to rise like this to a very high value, you must defy gravity, right? If g is very large, gravity is very strong, then even though you spin it, it's not going to go up very much because gravity tends to pull it down, keep it down. So indeed, when g is large, k is small. That makes sense. Now what about t squared? It turns out that k is inversely proportional to t squared. And what if it does not spin at all? If the bucket is not spinning, what's t? No, t will be infinity because it takes forever to spin around because you're not spinning. Okay, when t is infinity, what's k? K is 0. So y is equal to 0, which means the water is perfectly flat. That makes sense because you're not spinning the bucket. Of course the water is not going anywhere. It's not spinning. And then gradually as you spin it, and if you spin it pretty fast, then t is short, right? When t is short, k is large. That means it's going to grow to a situation like that. And then you make it even faster, spin it even faster, t is even shorter. It's going to look like that. Okay? It curves even more. So qualitatively, that makes perfect sense. You can also check the units of k. You see, you have meters per second squared, that's for g, right? And you have t squared, which is second squared. Everything is in the denominator. So in the denominator, second squared cancels, that's 1 over meter. So the unit of k is 1 over meter. That's perfect because here you have meter squared times 1 over meter, you get meter. So that makes sense. Okay, so for whatever reason, suppose you made an algebra mistake and you find the answer to be g times t to the power 3, 1 over. That cannot be right because the unit would no longer be 1 over meter as desired, would have been 1 over meter over 1 second. That would be wrong. Okay, so it's important once you get the result to check whether it makes common sense, you know, how it depends on g and t, and whether it gives the right units.